So what I want to tell you about this afternoon is how we can design better processes by designing the molecules that work within those processes. And I'll do this by talking about the work that I've done here at Imperial. And of course, this work I haven't done by myself, and there are many, many people behind this work. And I'll start by acknowledging their fantastic contributions. Then I'll start by talking with an example about why molecules matter and what difference we can make to processes by changing the molecules we use in them. And then I'll explain how we've taken steps to develop methodologies to make molecular decisions in a systematic ways through two sets of examples, one in energy production and one set in the fine chemicals industry. And then very, very briefly at the end, I'll talk about what work we're doing in optimization to try and find the best answer to all these molecular design problems. Okay, so everything that I'll be presenting today, and much beyond what I'll be presenting, is really the work of many people, past PhD students from Haitao Huang, who started the group. It's a line of fantastic people, still continuing. Now these are the current students in the group, and supported and complemented by a fantastic team of postdocs working with me. And I'm really truly indebted to all of your hard work. Many of you are here tonight, and I'm very pleased to see you. In delivering the work that I'll be presenting today and making research so interesting. I'm also really fortunate to have a fantastic set of collaborators. Some of them are listed here from Imperial and elsewhere. A lot of my work, as Andrew mentioned, is in the area of molecular systems engineering, and you've got a photo of the 6 academics involved in this here. I was receiving the Research Excellence Award from Imperial in 2010. We started working together around 2000, and it's been fantastic growth and fantastic fun working together. And of course, the work wouldn't happen without the industrial collaborators and the funders who make it possible, both in terms of providing the money to fund the work, but also in terms of providing the inspiration and the real problems that we try to tackle. Okay, so whenever I present things, think of all these people who have made fantastic contributions to the work. Okay, so as I said, I want to motivate a little bit why molecules matter to process design. And I'll do that by looking at the very first industrial process I looked at when I started at Imperial, which was provided by some colleagues at Syngenta. And they were looking at a separation just after a reaction where they had the product which they wanted to recover, dimethylacetamide as a solvent to be used in a further reaction, and there was some water they wanted to remove, as well as using hexane as the solvent to extract this water from the system. So this was a batch separation, and so this mixture goes into a batch separation and is heated up, and eventually the hexane and water come off, and the hexane is separated from the water in a decanter. And there are a number of constraints in making this process work in terms of having very little water in the product stream that comes out, in terms of having only water in the stream that comes out of the decanter here, and some limits on the temperature that we could use here in order to avoid decomposition of the product. Okay, so if we want to improve this process, to improve the performance of this process, looking at the overall process, it appeared that this step here was a bottleneck. It was taking the longest. And so if you wanted to shorten the time to do this, you might try to change the reflux ratio, the Ribolio duty, in order to minimize the separation time. And in doing that, you'd find that it takes 18 hours to effect this separation. Okay? But now, can we do better than this? And in particular, can we change the solvent molecule in order to reduce the time that is needed for this process to take place? So we have to then have a different molecule going through all the relevant streams of the process. Okay, so we can start trying different molecules. So we had hexane to start with, 18 hours. We can try pentane, and it turns out that we can't meet the process requirements with pentane. We can keep trying, maybe methoxypentane, and that doesn't work either. And maybe next toluene, and lo and behold, toluene manages to complete this process in 15 hours. So yes, With a different solvent molecule, we can have a 15% gain in productivity. That's 40 days per year in productivity gained. Okay? So really, the problem we want to solve when we're trying to accelerate this process is not only can we find the reflux ratio and the reboiler duty that are going to optimize it, but also can we find the solvent molecule that is going to give a faster separation. Okay, so that's the problem we really want to solve. So how can we solve it? And to do that, we need to define what I mean by best behavior and understand what are the challenges in trying to solve such a problem. Okay, so in using traditional chemical engineering tools, we would manipulate the operating conditions. We can change the design of the units or the topology of the process. But we'd also like to change the molecules. Okay, and so as soon as you change a molecule, you need to be able to predict what properties you're going to have in your process. And this can be, for example, whether you have phase separation or not. Okay, and this will be affected by the molecules that you change. And here, you have, in fact, one of the first examples of what I mean by best behavior, which will crop up during the talk. And what you find is that for a given temperature and pressure, the mixture is going to find itself in the configuration that minimizes its Gibbs free energy. And so this is its best behavior, whether it separates into two phases or is in single phase, will depend on trying to reach this minimum. And we'll see that it's very important to be able to solve this problem in order to solve the overall molecular and process design problem. Okay, once we can predict the properties and predict this best behavior for a given molecule, we can then look at the performance of the overall process and understand whether we are meeting our objectives or not. So that's the other kind of best that I want to look at, whether we have achieved the best performance out of the process. Okay, what is very important in trying to solve this problem is the interaction between the properties and the operating conditions. So we can't decide on one and then on the other, because if we change the temperature and pressure, we will change the behavior of the mixtures. Okay? And if we change the behavior of a mixture, we'll change what is best in terms of the process. And this interaction makes the problem very challenging. Nevertheless, we like to explore possibilities in terms of molecules, and instead of trying one molecule at a time, what we're going to try and do is to try and build molecules from building groups. So we're going to take atom groups and try to combine them to get to the best answer. How difficult is this? Well, let's take, for example, 20 different building blocks. And we're going to make a molecule which has up to 10 building blocks, and we can use 10 blocks of each type, let's say. So we can make a molecule with only one block, one type of block. And so how many possibilities are there? This is a very basic approach. We're not looking at the chemical meaning of these entities, but there will be over 1 trillion combinations possible. We can quickly eliminate some of these because some of these combinations will not be physical. But still, if we just spent 1 second evaluating each feasible option, it would take thousands of years to evaluate all the feasible options. So that is not going to be manageable. We have a combinatorial problem to deal with, and we need some specific tools to deal with it. Okay? And we don't want to give up. Okay? And we don't want to go randomly through this haystack. And so what a lot of my research has been about is trying to develop systematic methods in order to find the best molecule, as opposed to searching randomly or with luck. Okay, so what ingredients do we need to put together in searching for answers? Okay, because we have so many possibilities, we're going to use a computer to try and get to the solution. And so we need to frame our problem in mathematical terms. So we need to pose this problem and capture all of the constraints and our objectives in a mathematical formulation. We are then going to need models with this mathematical formulation, which are going to relate the molecular structure to the properties. And then once we have that, we need models that relate the properties to the performance of the overall system, whether it's a process, for example, or a single unit. And finally, once we've got this modeling framework, we need to be able to find the best molecule, and that's going to be the role of optimization techniques. Okay? And so what I'm going to do now is talk to you about all of these ingredients and how they can be developed and come together through some specific examples. And I will start by looking at energy production with 2 examples in this area. And the first is the production of natural gas. Increasingly, as we try to exploit gas fields, we find that they contain a high proportion of CO2, up to 50 mole% in some reservoirs. And in order to make economic sense of digging this gas out of the ground, we need to make sure that we can remove this large amount of CO2 economically. Okay, so here is a process that we might use to do this. Okay, one thing that we have working for us is that the gas comes out of the ground at a very, very high pressure, 80 times atmospheric pressure. And so we have a mixture of natural gas and carbon dioxide, let's say 50-50 mixture. And we're going to put this through an absorber. And in this absorber, we're going to have a solvent, which is going to come down and absorb the carbon dioxide, producing clean gas at the top. The solvent contaminated with the carbon dioxide is then going to be regenerated here in the flash unit. We're just going to let down the pressure and let the carbon dioxide come out as a gas and recover our solvent here. And the solvent will be going around in a loop from contaminated solvent to clean solvent here. Okay, and we may have some solvent losses, and so we'll need to top that up as well. Okay, so we have some constraints, of course, on designing this process. We'd like to have less than 3% carbon dioxide, for example, in the natural gas. We have size restrictions on our absorber. We want to make sure that all of the solvent is above its freezing point, so the temperature never becomes too low, so that it can keep flowing through the pipes. Okay, and so this constrains what we can do. But we do have some degrees of freedom as well. And so, for example, we can change the pressure at which we operate the absorber. We can change the pressure at which we operate the flash. We can change the flow rate of a solvent. And importantly, we can change the molecular structure of a solvent. Okay? And here is a very good example of how we have interactions between the process and the molecule and its properties. In order to be able to know how this process performs and how much gas we are making and how much money we're spending on the capital equipment here, we need to know about the phase equilibria between the CO2 and the solvent and how much CO2 is absorbed, how much natural gas is absorbed as well. We need to know the vapor pressure of the solvent to know if we're going to lose much solvent through here, for example. And we need to know the viscosity of the solvent to make sure that things are going to flow well. Okay? So physical properties are going to be key, and a large part of the effort that we have in the molecular systems engineering group is dedicated to a prediction of physical properties in a way which is going to enable us to do molecular design. And this area of work started for me when I joined Imperial. It started long before, and my colleagues Amparo Galindo and George Jackson, as well as Andrew Burgess, who is here today, developed the SAF-VR square well equation. So SAF stands for Statistical Associating Fluid Theory. And square well denotes the way in which the spheres here interact. So molecules are represented as a group of spheres, a chain of spheres, and they interact, in this case, for a square well potential. And one thing we've done is looked at how you can change the potential of interaction between these molecules and what effect that has on the accuracy of the calculations that you do. And if you take an example, for instance, perfluoromethane here, you can see that it has a very large impact on the properties you predict. So for instance, here we have vapor pressure, we have density, and we have heat capacity, all as a function of temperature. The symbols are data points, and the black lines are the calculation using this Mi potential here. The red lines are calculations that you obtain using a different interaction between the segments. Okay? So you can see that this has a big impact, and this sort of thing allows us to then represent accurately the behavior, the phase equilibria of carbon dioxide and methane, which is very important to the development of the natural gas recovery process. Okay, so we do this well, but what we need is something more predictive, because in this case, we're looking at molecules as a whole, but we need to be able to build molecules from these building blocks. And so here, we developed a theory which allows us to represent molecules as sets of groups within the same SAF framework. And we combine these two advances in order to develop SAF gamma Mi, which here is shown predicting the behavior of mixtures of CO2 and alkanes, where all the alkanes that you have here, you have propane, butane, decane, are built up as groups of CH3s and CH2s. Okay. What we're doing with this theory now is continuing to expand its capabilities by building up the set of groups that you can represent, and therefore the number of molecules that we can build. And also, in order to be able to do this, we're using algorithms that we have developed for phase equilibrium and parameter estimation to solve the complex problems that are needed to identify what the group parameters are. Okay, so we have a large effort in this area for different applications. And what I want to show you here is how we apply this to the case of natural gas separation. Okay, so we come back to our problem. And this is the solvent space that we're going to use. So we're going to use very few groups at this point, just the ones necessary to make up alkanes and some ethers, different types of ethers. The glymes here are already used in CO2 recovery from natural gas, and so we know that they work quite well. And what we're looking at also is much more oxygenated compounds to see if the oxygens here can improve the separation even further. And here I've shown you specific molecules, but we're building them from groups so we can change the chain length. And so the question is, which is the best solvent for this process from an economic perspective? Okay, so with this set of group here, we have about 250 solvent candidates that we could potentially design. And we can assess these economically, but first we can have a look at the properties and some indication of how they're going to perform. So the things that are going to be important to the economic performance of the process are the flow rate of gas that we're able to produce, which increases in this direction. So these solvents are better here. It is trying to minimize the flow rate of solvent around the loop. So we're trying to go to the bottom here. So this corner would be ideal, really, because this will minimize the capital cost of the equipment. And we also want to minimize the solvent losses, which is basically the blue-green colors, so these kinds of solvents here. Okay, so this is some indication, and each point that you have here, looking at these criteria, is the best solvent that we have found to achieve that performance. Okay, but if we look at it in terms of money and estimate the operating and capital cost on an annual basis for the process, and we designed for the best solvent, if we just restrict ourselves to the alkanes, we find that the best alkane, C14, gives us a profit of $90 million per year. If we go for standard solvents, then the best glyme gives us $130 million per year. But if we then extend the group to all the solvents I showed you, the 250 solvents, then the profit is $150 million per year. Okay, so you can see the very significant impact that we have here. And the main factor here is the gas production flow rate. Okay, so here is a complete story of how we can design the process and the solvents at the same time. Of course, together with each solvent, we have pressure for the absorber, pressure for the flash, etc. Okay. Now, can we take this to other problems? And we have, in particular, a problem in carbon capture from power plants, which is an increasingly important problem. Fossil fuel power plants are responsible for the vast majority of CO2 emissions, and we have a target to reduce these emissions quite quickly, and so we need some short-term solutions for this. And absorption processes are a promising option. So we're going to do something quite similar to what I've just described, except that now the flue gas contains very little CO2, and it is at 1 atmosphere. Okay, so we haven't got pressure working for us. And so what we're going to have to do is to use a solvent which reacts with the CO2 in order to absorb it at ambient pressure. And so, although that works well, it makes the recovery of the solvent much more challenging. And so now we have to use a desorber to clean our solvent and separate the CO2 at the top. And we have to use a lot of energy for this reboiler in order to be able to regenerate the solvent for it to go in a loop. Okay? So this presents some more challenges because of the reactions. The physical phenomena are much more complex. And so this is for a given solvent, a set of reactions that go on in the desorber and in the absorber. And what you have here as R is what makes the identity of a solvent. The most common solvent is monoethanolamine. So this is the R for this solvent. What you see is that we have now 13 species involved in these reactions. We have to worry about reaction kinetics. We have to worry about reaction equilibrium and also phase equilibrium. So many more phenomena. And anytime we change the solvent, everything in this blue box changes. And so what that means is that if we want to develop a model for a given solvent here, we need a lot of experimental data. And this really is a challenge in terms of solvent design. Okay? So what we're going to do is instead of trying to model the whole complexity of this, is to try and take a simplified view. And we're going to look at just 3 components instead of the 13, CO2, water, and monoethanolamine. We usually use aqueous solutions of amines. Okay, so water is always present. And represent the reactions within the SAFT formalism through sticky sites here, which allow the molecules to come together and form aggregates. Okay? And so, for example, here's an example of one reaction and how we represent it as with the product as an aggregate of CO2 and the solvent. Okay? And this gives good results in terms of predicting the thermodynamics of these mixtures, these quite complex mixtures. So this is the partial pressure of CO2 as a function of the amount of CO2 in the liquid phase. And so this data are used to develop the model, whereas in this case, we're predicting with the model how much carbamate is formed, this is the red line, and how much bicarbonate is formed here. And you can see that these predictions are in very good agreement with the symbols, which are the experimental data. Okay, so this simplified approach gives a good representation of the thermodynamics of this mixture. Now we need to put this into our process model. Okay, and so we have this simplified view of the thermodynamics, which goes into a model of what's happening in the absorber. And here again, we have very complex phenomena. So the mass transfer, for example, is quite challenging to model. And we do model this in a lot of detail in this case. Okay? And it is the fact that these phenomena are dominating the process, which allows us to take a fairly simplified view here. Okay? And this is helpful when it comes to solvent design because we have a much simpler thermodynamic model and therefore a much simpler relation to molecular structure than if we went for the full detail. Now, we've made simplification, so does it work? Well, we do use a bit of pilot plant data to parameterize this overall model. We have one parameter, and we use one pilot plant run to parameterize it. And then we go and predict different runs. So this is, each row here corresponds to a different pilot plant run under different conditions, flow rates, etc., as predicted with our model. And so we have here the liquid temperature as a function of the stage in the absorber. So as you go through the absorber, the mole fraction of CO2 in the vapor and the amount of CO2 in the liquid. And you can see that in these different pilot plant runs, we get good predictions of what the behavior of a process is. Okay, so we're doing well for MEA as a solvent for monoethanolamine. So now what we want to do is to use this simplified model and move to different solvents. And so we're always going to have CO2 and water. And we've been building up our set of other molecules that we can use. So here is a list of the ones we've got so far. And this allows us then to design blends of solvent blends, which can be more effective than single molecule solvents. And the other thing that we've been doing is building up some basic groups in order to be able to build new molecules. And so, for example, we can make a mixture of N-propanolamine and water from our building blocks here and predict the phase equilibria. Okay? And I'm not going to be able to tell you today what is the best solvent for CO2 capture from flue gas. This is the point where we're at, which is a very exciting juncture. We're at a point where we can start designing mixtures, we can start designing new molecules in order to improve this process. And we're starting to work with experimental colleagues who can then test the hypothesis that we make in terms of what are the best solvents. Okay, so in terms of what we've learned from working with energy production problems, I think hopefully I've convinced you that process design and molecular design are a problem that should be considered together, two problems that should be considered together. And that when it comes to property models, we need transferability and we need just the right level of detail. So we need sufficient accuracy to get the impact of the molecular structure on performance. Okay, but we need to sometimes make compromises in terms of accuracy in order to have transferability. Okay. Now I've talked a lot about vapor-liquid equilibria, and I now want to turn to a different industry, the fine chemicals industry, in which solids play a prominent role. Okay. So you can see here on this picture a lot of medicine, and they usually come in solid form. And this really has a big impact on performance. So performance in terms of the drugs you take and how effective they are, because they must dissolve in the body, and different molecules and especially different crystals dissolve in different ways, and this affects whether the drug is effective or not. And the fact that they come into solid also affects the way that you manufacture them. So the process aspects are important as well. We are going to want to do our processing mostly in liquid form, and so we want to dissolve the molecules into some solvents, and the solubility is going to be very important, and the impact of a solvent on the physical process is going to be very important. Okay, and I'll show you some examples of that. So we are going to be concerned very much about what happens in terms of solid-liquid equilibrium. So here is a phase diagram for benzene and hexadecane as a function of temperature at 1 atmosphere and the mole fraction of benzene here. And we have, at high temperature, a liquid phase, and then as we cool things down, we have solid phases appearing. Okay, and you have here on the left hexadecane in its solid form. So this is the most stable crystal structure of hexadecane, and here is benzene. Okay, so we need to be able to model both the liquid phase and the solid phase. And I will start with a solid, which is extremely challenging because molecules can pack in many different forms. And this phenomenon of them packing in different forms is called polymorphism. And different forms of packing have different properties. They have, you can see a few of them here. They can have different colors, but they will have different solubility in a given solvent. Okay, and this is a very significant issue in the pharmaceutical industry. For example, here is ritonavir, which is a HIV drug manufactured by Abbott Labs. They started manufacturing it in the late 90s, and they were manufacturing it in Form 1, which was working very well. And after some time producing it, all of a sudden, Form 2, which is a different crystal structure, started being produced. And it turned out to be more stable than Form 1. So they could never go back to making Form 1. Why was that a problem? Because Form 2 not only is more stable, it is also less soluble, which means that it is less effective as a drug. And so it had to be recalled from the market, and they had to find a new formulation for this drug. In the end, they produced it in a form which has to be refrigerated. And so whoever is taking this drug now needs to have it in refrigerated form, which is rather inconvenient and also poses issues in terms of quality control of the drug. And so this was a huge cost and a huge inconvenience for patients. And so it's something that people would like to be able to control. Now, when this happened at Abbott, one of the people involved made a very striking statement about what polymorphism can do. Eugene Sun said that there are many mysteries of nature that we have not solved. Hurricanes, for example, continue to occur and often cause massive devastation. Meteorologists cannot predict months in advance when and with what velocity a hurricane will strike a specific community. Polymorphism is a parallel phenomenon. This is a very strong statement. We know that it will probably happen, but not why and when. Unfortunately, there is nothing that we can do today to prevent a hurricane from striking any community or polymorphisms from striking any drug. So is there nothing really that we can do about this? Well, of course, this is a great challenge for researchers, and there has been research in this area of crystal structure prediction and trying to understand what polymorphs can exist for quite a long time. In 1999, there was a blind test done where several groups from the community were invited to try and predict what structures might be stable for crystals, for molecules for which the structures had not yet been published. And so those structures are shown here. And you can see, so what this shows is a number of groups who participated. 11 groups tried this molecule, and 4 were successful. In this case, 1 out of 8. So you can see that there are a few successes, but they were not consistent through all of the participants. Okay, and this is an extremely challenging problem. The solution to this problem requires finding the minimum energy for the crystal, so the arrangement of the molecules within a repeating unit, a unit cell, and the positions of the atoms that minimize the energy of the crystal. And so it's important, if you want to control polymorphism, not only to find the global minimum, but also local minima to this problem. And so in collaboration with Kostas Pantelidis, we've been developing a methodology for crystal structure prediction, starting from molecular connectivity here, just knowing the diagram for the molecule, to being able to find its polymorphs. This is the Roy molecule, red, orange, yellow, which has 10 non-polymorphs. And you can see here that they have very different physical appearance as well as different physical properties. Okay, and the way we approach this problem is that we start by considering what conformations the molecule can take, and also its charge density through quantum mechanical calculations. And here the details and the accuracy of these calculations are very important. We combine this with more empirical models of the interactions between the molecules, the longer range dispersion interactions. And this is combined within an algorithm called Crystal Predictor, which does a very, very extensive search, and which was developed by Panos Karametsanis and Kostas Pantelidis at Imperial. I then got involved in this area, working with Panos Kostas and Andrei Kazantsev, and also using the code of Sally Price at UCL. And we developed a code called Crystal Optimizer, which takes the results of this algorithm here, the best results, and for each one of those uses a more accurate model to try and re-rank and identify in which order, which is the lowest energy structure, and to refine all of the structures. And so from that, then we can postulate which are the most stable structures. Okay, so we've applied this algorithm, this overall methodology, to quite a few problems. In 2010, we took part in the blind test, and with Sally Price worked on this molecule here, molecule 20, which was the largest molecule ever considered in a blind test. And we were one of two groups to manage to predict its structure. And what you can see here is an overlay between our prediction and the experimental structure. Okay, so we were very pleased to be so close to the experiments. We also looked at a molecule provided to us by a pharmaceutical company, BMS. And this is quite a flexible molecule here. And what you have here is a lattice energy landscape. So this is lattice energy, the lower the better, and the density of the different structures. Every point that you can see here is a different potential crystal structure. And then you have two experimental forms, form 1, which we found here, and form 2, which we found here. So this looks great. But if I look a bit more closely, you can see that below this structure here, there is another one that we have found and that they don't know about. So the question is this structure real, or is it an artifact of the calculations? And so we're working to try and increase our confidence in the calculations so that we can either eliminate structures like this or say with confidence whether they should be found experimentally. There's a lot of work that goes into this. The results that I've shown you are based on the work of Panos Karametanis and Andrei Kazantsev. And we have a team of people continuing to work on this. And I just want to highlight a few very recent results from Manolis Vassiliadis on including temperature effects. All the calculations that we've done so far are at 0 Kelvin and neglect temperature effects. But he's been developing lattice dynamics calculation in order to be able to calculate the free energy and really take into account temperature. And so he's looked, for example, at this molecule here, tetracyanoethylene. And so this is a lattice energy landscape at 0 Kelvin. And so here again, all the structures, and here are the best ones we found. And so the lowest one is the cubic form, which turns out to match the experimental data. And we found less stable a monoclinic form here, again, in agreement with the experimental data. With his new calculation, he's been able to go to 300 Kelvin, and this is a modified energy landscape at that temperature. And the color coding here indicates how much the structures are moved up and down in the landscape. And what is striking here, with the dark blue being a very large shift downwards, you can see that a lot of the structures that are now at the bottom are in dark blue. They have moved a lot. So there's a huge amount of re-ranking that goes on at 300 Kelvin. Okay? And in this case, Manolis found that the cubic structure has moved up quite a bit and is no longer the most stable, and that the monoclinic structure is now the most stable, in agreement again with experimental data. So we're very excited about these results. Okay, so we're making progress to understand and predict how molecules behave in the solid, and this will help us to understand then the solid-liquid interface and how molecular structure affects solubility and how changing the solvent might be appropriate for one drug or another. Okay, the next thing I want to do is to now move to the liquid phase and to talk about the impact of solvents in terms of processing. So in the fine chemicals industry, solvents are used very frequently, as I mentioned earlier, because most of the molecules of interest are solid. And this comes at a high price. For every kilogram of active ingredient, so the drug that people take, for every kilogram of active ingredient that is made, we need to use 4 kilograms of solvent. Millions of solvents, of tons of solvent are used every year, and this has a big impact in terms of the energy cost of the processes. 60% of the energy is devoted to solvents, often because of the separation processes, and 50% of the greenhouse gas emissions come from the use of solvent. Okay? So there are a lot of issues around solvent choice in pharmaceutical and agrochemical processes. And I talked about an example right at the beginning with the batch separation. One problem that has been of particular interest is trying to accelerate reactions by solvent design. And it's an area of work that I got involved in very early on when I started at Imperial. And about a couple of years ago, we finally managed to solve the first real problem. You know, the way I imagined it in 1999, we managed to solve it a couple of years ago. So it's been a long journey, but I'm very happy with where we've got to. And so I've been working in this area, in particular with Amparo Galindo, with Paul Taylor from Warwick, and with Alan Armstrong from Imperial. And Paul Taylor got me in the lab to try and actually understand solvent effects on reaction. And we looked together at catalyzed reaction, Grubbs catalyzed ring closing metathesis reaction, and we did measurements in different solvents. And this took quite a lot of effort, but here are the results that we got in terms of the impact of the solvent. So what you have here is the concentration of the product as a function of time for different solvents. And you can see very striking differences. So if you take, for example, acetone, which is the pink solvent here, you can see that things start off really well, and the reaction proceeds very fast, and then it tapers off. And what's happening here is that the catalyst is being deactivated in acetone. And so there's only so much of a reaction that can proceed before it stops completely, and there is no catalyst left. In the case of dichloromethane, things are going very, very slowly, but if you wait long enough, the reaction will go to completion because there is no deactivation of the catalyst in this solvent. In acetic acid, however, things look great. The reaction goes to completion very quickly. The one thing you can't see in this picture is that the catalyst is not very soluble in acetic acid. So you need a lot of acetic acid to get reasonable quantities of product. Okay, so we have some very complex trade-offs. And the one aspect that I want to focus on today is just how do we get the fastest rate constant here? How do we get things going as fast as possible? Okay. And so how do solvents affect reaction rates? Well, in a reaction, the reactants are going from an energy minimum to an even better energy minimum through rearrangements. And the way they get there is by going through this energy surface here, and they have to go over some barriers via transition state. And what happens once you change the solvent is that the height of this barrier is changed because the reactants and the transition states are more or less well solvated by different solvent molecules. Okay, and so what we'd like to be able to do is to identify a priori or through computations which solvent is best for a given reaction. Okay, and as I said, this was a very long journey. We knew that we needed to use quantum mechanical calculations, so we just started off by proving the concept that you could use quantum mechanical calculations in molecular design, okay, without getting to the reaction rates. And we wanted to also be able to optimize rates, and what we showed is that you could take a few experimental data points here in different solvents, build a simple model of what was happening, and find a better solvent. Okay, and we somehow needed to combine these two pieces of work here. And so this is what we've done recently. So starting from our building blocks, we now calculate the rate constant in different solvents, which we make from our building blocks accurately with quantum mechanics. We then build an approximate model of what is happening, which allows us to change the structures of a solvent very cheaply in a matter of milliseconds rather than the hours that it takes to do these calculations. We then put this in an optimization problem and find the solvent that maximizes the reaction rate. If we have found an improved solvent from what we had previously, we go back and check that that our approximate model was right, and we re-optimize until we can find no better solvent, at which point we go and do some experiments. Okay? So this is the overall methodology that we've developed, and we've applied it to a couple of reactions now. And the first one we looked at was a Menshutkin reaction of phenacyl bromide and pyridine here. We chose this reaction because it's very well known to have large solvent effects. And we started with a fairly large solvent design space of 1,300 molecules. And we started doing accurate calculations in a few solvents. And you can see, this is the rate constant. You can see the effect of a solvent is very large. And so we went through our procedure. And after 10 quantum mechanical calculations, so the first 6 and the 4 more here, we found that nitromethane gives the fastest reaction rate with an increase of 40% over the best solvent we started with. Okay. So this is all calculations. does it really work? So this is our simulated batch reactor with the initial solvents. The dotted line here is experimental, and the solid line is our prediction. For the slower solvent, we don't do so well. And when we went and tried nitromethane experimentally, so this was our prediction with quantum mechanics, and what we measured was even better. And indeed, it is a better solvent than the one we started with. So we were very pleased to see this. And this last step of bringing everything together happened thanks to Heiko Schrubing and Zara Ganais. And we're now continuing to develop the methodology in different ways, in particular looking at incorporating temperature effects in this framework, but also improving the algorithms and the range of solvents that we can deal with. Okay, so the fine chemicals industry presents some very interesting challenges. Solvation really is at the center of what we're trying to do in this area in terms of understanding the solid phases and the liquid phases. And here you really do need fine details in the calculations in order to be successful in your predictions. And so a lot of what happens in terms of being able to find solutions despite the cost of the calculations is based on using mathematical tools such as approximate models and sophisticated optimization algorithms that allow us to explore the space very quickly. Okay. And so the last thing I want to talk about very briefly is optimization. I won't spend much time on it, but I wanted to say a few words about it because it's really where I started. I did my PhD with Chris on global optimization. And as you will have had a sense from the talk, it's not enough to say that you want to find the best solution. With nonlinear models, you often have many solutions that look very good. They're all minima. And so this is an energy surface, but it could be any nonlinear optimization problem. We have multiple minima, and here a global minimum. Okay, and so we need algorithms to find this global minimum, often because the global minimum is the only meaningful answer. For example, if you're looking at vapor-liquid equilibrium, it is the only answer that matters. Anything else is unphysical. If you're looking at whether you have hotspots in the process and whether your process is safe, knowing the maximum temperature a process can achieve is the only safe answer. And if you're looking at it from an economic perspective, finding the global optimum is really the answer you want. It's the best answer. And the only way to be sure that you have the global minimum is to use a deterministic global optimization algorithm. Okay, these are algorithms that absolutely guarantee that you have found the best solution. And these algorithms require quite a lot of understanding of the mathematics underlying the problem. And so they're not applicable to all problems yet, but we're trying to push forward these algorithms as we go along. Okay, and so I dug out a slide which I prepared when I was doing my PhD with Chris here, which highlights some of the concepts of the global optimization, these global optimization algorithms. Okay, and we're dealing with non-convex objective functions, non-convex feasible regions, and the trick here is to try and build convex relaxations, some simplified problems which have a unique solution. So whereas you have many solutions here, we have a problem which gives us a unique solution and has a specific property. In particular, we know that this solution is lower than the solution of the original problem. Okay, and what we then do is use a divide and conquer approach to try and find the very best solution. Okay, and I want to use this slide really as an opportunity to say thank you to Chris for getting me started in research and also for providing a lot of inspiration. When I was doing my PhD, Chris was getting involved into protein folding, and so there were a lot of molecules floating around in the lab, virtually speaking, and I think this sparked also my interest in things molecular when it comes to process design. Okay, we are continuing to work on this, and there's quite a lot of work going on in the group, which I haven't got time to acknowledge today. I just wanted to show you a little example of us continuing to try and work on building better convex relaxations, better underestimation. So here is a typical test function, which has 121 minima, and so we use a divide and conquer approach to modify essentially the surface, and as time proceeds, to narrow in on the global minimum for this problem. And the game here is to try and do this faster and better so that we can solve more and more realistic problems. Okay. And so hopefully, through this rather quick tour of the work over the last 15 years or so, I've convinced you that molecules matter to process design, and I've shown you what ingredients are needed to solve this problem successfully. in terms of mathematical formulation, in terms of having models that are predictive all the way from molecular structure to performance, and in terms of having optimization tools that can solve these complex nonlinear and combinatorial problems. This wouldn't happen without all the people who have been involved in there. So, of course, all the people who have worked with, I've been really fortunate and privileged to work with all of you. Also, all the support people here who make research possible at Imperial. And I'm also really pleased that my parents are here today and my family, and I want to thank them for the trust and support that they give me throughout my career. And thank you to you for your attention.